All right, everyone, so looking at this first example, we are given the function f of x equals x squared minus 3x plus 1, which is a quadratic. So I've went ahead and typed that equation into my calculator, and we can see that our quadratic looks like this. So what we want to try to find for this problem is f prime of 3. So we want the slope of the tangent at x equals 3. So if I use the trace button on my calculator and say, well, where are we at x equals 3 on this quadratic? We can see that we are at the point 3, 1. So my tangent point is 3, 1. So what we are going to be doing is trying to find the derivative of this quadratic at the point 3, 1. So if we imagine drawing a tangent line that goes only through this point, so it's just touching at that one point and is tangent to the quadratic, we want to visualize what the slope of that line would be. One thing that we can tell from looking at our calculator is that it is going to be a positive slope since it is going up and to the right. We also can see that it will be fairly steep. So I like to do this on my calculator because it kind of helps me visualize what it is that I'm looking for, and it's also going to be a useful way of checking yourself, especially in regards to sine. For example, if we went through this whole process and I got a negative slope, I either found the slope at a different point. So for example, a tangent point over here would have a negative tangent slope, or it means I goofed somewhere with my sine. So you don't have to type it in on your calculator, but for these first few examples, this will kind of be a nice way of checking ourselves. So using the limit definition of the derivative, and this is exactly the work that I will be looking for on the written practice set, so no shortcuts. You have to have this limit definition of the derivative for calculus. We start with f prime of x, which in our case here is going to be f prime of 3. So later on, we'll find a generalized formula all in terms of x for the derivative, but for these examples on this page, we're going to be looking for the tangent slope at a particular point. So we start with f prime of 3. And this is equal to the limit as h approaches, the limit as h approaches 0. Ignore that. And remember, this limit part of the definition just says that the h, or the hair beyond, the tangent point. So think back to that visual that we talked through in the previous video, or that activity that we did on the previous page. This essentially says that as we close in on the distance between the tangent point and any given point on the curve, so as I move closer and closer and closer to that tangent point, or as that distance between those 2 points approaches 0, we are going to get closer to our tangent slope. So make sure that you always include this limit notation with every new line of your work. So we are going to carry this limit through for this entire first line. In calculus, they actually make you write that limit as h approaches 0 with every single step of your work. To save us a little bit of time, we're just going to rewrite it anytime we drop down to a new line of work. So the limit as h approaches 0, and then we simply write our slope formula that we talked about above. So our slope formula, we start with the y value of our hair beyond point, so f of x plus h. So remember, f of x is the same as y, f of x plus h, because that's the corresponding y value that goes with our hair beyond point. Then minus f of x all over x plus h minus x. So remember, this part of our definition is simply the slope between the 2 points. And lucky for us, we can actually cancel out that x with that negative x, which means less writing later. So what we have just written is the limit definition for the derivative. So f prime of 3 equals the limit as h approaches 0 of f of x plus h minus f of x, the change in the y values, divided by x plus h minus x, or just h, which is the change in the x values. So this, to me, is kind of the toughest part about these problems, is just doing this very first step and getting this limit definition of the derivative memorized. From here on out, it's really just a matter of doing substitution of what we are looking for. So moving on to our next step, and remember, we're carrying that limit as h approaches 0 through this entire horizontal line of work. So we're going to focus on our slope part of the definition, f of x plus h. So first, instead of x, we are going to be plugging in 3, since that's the specific x value we are looking at. So f of 3 plus h minus f of 3. And then all over just h. So easy enough, we just plugged that 3 in for each of the x's. So now what we are going to do is actually evaluate the function in terms of these two different inputs. So if I wanted to find f of 4, I'd plug in a 4 everywhere I have an x. If I want to find f of 3, we'll plug in 3 everywhere we have an x. So if I want to find f of 3 plus h, we are going to plug in 3 plus h into every x in our function. So in our first line, f of 3 plus h will be 3 plus h squared minus 3 times 3 plus h plus 1. So f of 3 plus h, we took the 3 plus h and plugged it into our function. So 3 plus h squared minus 3 times the input, or 3 plus h, and then plus 1. So f of 3 plus h is this entire expression. Oof. Next, we are going to subtract, and folks, that minus sign in between your hair beyond points y value and your tangent points y value, I always kind of think of that as a good anchor point in my work. So sometimes I actually draw a box around that minus sign so that when I'm checking, I can make sure that I have all pieces of f of x plus h and then all pieces of just f of x. So that minus sign, I think, is very helpful. Now, for the next part, when we evaluate f of 3, we're simply going to plug 3 in for the x values in my function. So this is going to be a little bit easier. So 3 squared, and for the first x, minus 3 times 3 for the next x, and then plus 1 at the end. Now, there's one thing that we are missing in the step that we just wrote, and that is parentheses. We have to have parentheses here because I am subtracting this entire expression. I'm subtracting f of 3, so I have to subtract this entire expression. Now, here, it won't be as big of an issue because we are going to get just one solid point. But once we start finding the equation of the derivative, then we're going to really want to make sure that we have those parentheses there. And then this is all over h still. Woof. So we used our limit definition of the derivative to write our expression in terms of the tangent value's x value. And then we plugged in those values into our f of x function. All right, so take a deep breath. And we are now ready to drop down to the next line. Now, since we are starting a new line of work, we have to rewrite that limit notation. So the limit as h approaches 0. And now we're going to go ahead and start simplifying this expression. So let's start with the light green portion. How am I going to simplify 3 plus h squared? If you said FOIL, you have made my morning. So when we have a binomial squared, this is 3 plus h times 3 plus h. So make sure you FOIL. So when I FOIL that expression, 3 times 3 gives me 9. 3 times h plus another 3 times h gives me 6h. And then h times h is h squared. Next, we are going to distribute that negative 3 to both 3 and to the h, so make sure you take that negative sign with it. So that gives me negative 9, and that gives me a negative 3h. And then we've got that sneaky plus 1 at the end. So this is the simplified version of what we underlined up here. Next, we have our minus sign, and again, that's going to serve as kind of our anchor point in our work. And now to simplify our dark green part of the expression, 3 squared is 9, minus 3 times 3 is 9, so 0, and then plus 1 gives us 1. So I'm going to be subtracting a positive 1. And don't forget, this is all still over h. So again, we plugged in our expressions, 3 plus h and 3, into our function, and we are now just simplifying the expression as much as possible. So now, our next step of work, we're just going to combine like terms and simplify further. So 9 and negative 9, goodbye. 6h minus 3h is going to be 3h. h squared, sorry, I shouldn't cross those off. We'll just underline those to show we added them together. H squared is just going to stay h squared. And then the positive 1 and the negative 1 cancel each other out. So I'm left with h squared plus 3h all over h. So can I simplify this further? No. So now we are finally ready to get to the limit part of this expression, the limit as h approaches 0. Now, in lesson B, on page 3, we talked about how we can use direct substitution to find a limit by plugging in the limit value into our function directly, but we also talked about factoring and canceling and what to do when we can't plug in that limit value directly. So if I see what happens if I try to use direct substitution here, we would be plugging 0 in for h. Ooh, and why doesn't direct substitution work? In fact, why is it never going to work in our derivative? It's because we're always going to have this h in the denominator, and plugging in 0 is always going to lead to something undefined. So direct substitution isn't going to work until we factor and cancel. So after you simplify, folks, you're always going to try to get rid of that h in the denominator. So if I look at this expression, how can we get rid of that h? We can do so by canceling the restriction. So similar to what we did with figuring out wholes and vertical asymptotes, we start by factoring the top of that expression by taking out an h. So h times h plus 3 all over h. And now that I can cancel out those h's, we can now do direct substitution. So once I get rid of that h in the denominator, I will no longer be dividing by 0, and I will be able to do direct substitution. So when I plug in 0, and folks, instead of drawing an equal sign, I'm going to draw an equal sign with an arrow, because once we plug in that 0, we are no longer dealing with this limit anymore. We are actually plugging it in and going to a straight evaluation. So we plug in 0. And we get plain old 3. So what equals 3? F prime of 3 equals 3. So all that crazy work, all that horrible limit definition stuff, and we just get 3. So what does the 3 represent? What this answer tells us is the slope of the tangent at 3 is 3. So at 3 was the tangent point that we were looking at, and the slope of the tangent is what the derivative is. So what's nice about this is on the previous page, I said that on that second My Math Lab assignment, you would be exploring point slope form. We not only can find the slope of the tangent line, we now can actually find the equation of that tangent line. So we're going to practice using that point slope form. So first, our tangent point, we stated above, is 3, 1. And that's going to be our x1, y1 in point slope form. Our slope that we just found is 3. So m equals 3. So point slope form, and again, you have this written up at the top of page 6 in your note packet, is y minus y1 equals m times x minus x1. So plugging in those values, our y1 is 1, our slope is 3, our x1 is also 3. So there's our tangent point. And when you simplify point slope form, it turns into slope intercept form. So if I distribute and then add that 1 over to the other side, we get y equals 3x minus 8. So this is our tangent line equation. And what's awesome about this is now we can go back to our calculator, we can go to our y equals, and we can plug in that tangent equation. And we can see, ta-da! This line is hitting that quadratic exactly at the point 3, 1. So there's my tangent point. Here is the tangent line, and the slope of that tangent line is 3. So folks, our focus with the derivative is just going to be finding this, the slope of the tangent line, but I wanted to show this over here because this is a good way to visualize what it is we have found. So give yourself a high five, because these problems, they are big, they are nasty, but you have just done the incredible thing of finding the slope of a line using just one point.